What if I told you that light is kind of like a superhero? It has two completely different identities. And the craziest part, you can never, ever see both of them at the same time. Now, this isn't science fiction. This is a real, fundamental mystery of quantum mechanics. And physicists at MIT have just put this century-old puzzle to the test with a level of precision that the founders of the field probably couldn't have even dreamed of.
Okay, so let's just dive right in. The big question that has been bugging physicists for more than 100 years is pretty simple. What is light? Is it a stream of tiny microscopic bullets we call particles, or is it more like a ripple spreading across a pond, a continuous wave? Well, the absolutely bizarre answer is it's both. And which one it decides to be depends entirely on whether or not we're looking. Yeah, seriously.
To really get this, we have to talk about one of the most famous experiments in all of science, the double slit experiment. It's actually pretty simple. Imagine you're shooting tiny particles, like paintballs, through two vertical slits. You'd expect to see two stripes of paint on the wall behind them, right? Makes sense. And if you send a wave through, the wave splits and the two new waves interfere with each other, creating this really distinct striped pattern. Simple setup.
Okay, so here's where it gets interesting. When we actually do this with light, we don't get two simple bands. We get that striped interference pattern. So you'd think, great, light is a wave, case closed. But not so fast. The truly weird part is that this happens even if you send the light particles, the photons, through one at a time. It's almost like each photon somehow goes through both slits at once and then interferes with itself.
But this is where reality just completely breaks. If you put a little detector right at the slits to try and see which path a single photon takes, to catch it in the act, the striped pattern just vanishes. It's gone. The very act of measuring, of just knowing which slit the photon went through, forces it to drop its wave identity and act like a boring old particle, leaving just two bands behind.
Now, this quantum weirdness wasn't some sideline thing only a few people talked about. Oh no, it sparked one of the greatest scientific debates in history, a friendly but really profound disagreement between two absolute titans of physics, Albert Einstein and Niels Bohr.
So this whole debate kicked off way back in 1927. Einstein, who really wasn't a fan of the spooky randomness of quantum theory, came up with this really clever thought experiment to challenge it. Bohr almost immediately shot back with a rebuttal, using his new quantum principles, and for pretty much a century, that argument has been debated and tested, but never, ever as perfectly as in this brand new experiment from MIT.
Einstein's whole argument was basically just common sense. He said, look, as a photon passes through a slit, it has to give that slit a tiny, tiny push, a little recoil. Think of it like a bird rustling a leaf as it flies by. He believed you should be able to measure that rustle to figure out which path the photon took without actually destroying the wave pattern. He wanted to catch light being a particle and a wave at the exact same time. But Bohr's comeback was that Einstein was missing the whole point of quantum mechanics. He argued that sure, you can try to measure that rustle, but according to the uncertainty principle, the act of measuring it precisely enough to know the photon's path would introduce just enough uncertainty somewhere else that it would completely wash out the wave pattern. Bottom line, you get one or the other. You can never have both. So fast forward to today. To finally settle this, scientists at MIT designed the ultimate version of this experiment. They took the whole idea and stripped it down to its most basic, fundamental quantum parts to create what they call the most idealized test of this debate ever. Now, to do this, they couldn't just use a piece of metal with two slits cut in it. No, to really test this idea at the absolute most fundamental level, they needed to build the smallest, most perfect slits you could possibly imagine. And their solution was just brilliant. Instead of physical slits, they used single individual atoms floating in a vacuum, held perfectly in place by lasers. Each one of these atoms acts as a perfect quantum-sized target for a single photon to scatter off of. I mean, this is the double slit experiment in its absolute purest form. So here's how they pulled it off. First, they trapped about 10,000 atoms and supercooled them, arranging them in a perfect grid, almost like a crystal, using lasers. Then they shined a really, really weak light on them so that only one photon would hit the atoms at a time. In this setup, any two atoms right next to each other could act as the double slits for that one photon. And then a super-sensitive camera would just record where that photon landed, building up a pattern, one photon at a time.
Okay, now here's the really crucial part, the key to the whole thing. They could actually adjust the lasers holding the atoms. If they held an atom really tightly, its position was very certain, and it was terrible at recording that rustle from the photon.
But if they loosened the laser's grip, the atom became fuzzier. Its location was less certain. And a fuzzy atom is much more easily rustled by a passing photon, which means it gets better at recording which path the photon took. This fuzziness was basically their control knob for turning up the particle-like behavior.
So, this brings us to the billion-dollar question, right? By tuning that fuzziness, the researchers could basically choose how much which path information they were going to get. So, what happened to that wave pattern when they started turning the knob and peeking at where the photon was going?
The experiment was set. The data was all collected. It was finally time for the quantum verdict in the 100-year-long case of Einstein versus Bohr. So, who was right?
And the results were, well, they were perfectly, beautifully clear. As they made the atoms fuzzier, they were able to get more and more information about which of the two atoms a single photon had scattered from. They were actually detecting Einstein's rustle.
And as they did that, the interference pattern, that undeniable signature of a wave, it just faded away in direct proportion. The more they knew about the photon's particle-like path, the less it behaved like a wave. It was a perfect, one-to-one, undeniable trade-off.
So, what do we take away from all this? Well, the conclusions are pretty profound. First, Bohr was right. It is fundamentally impossible to see both the particle and wave sides of light at the same time. Second, Einstein's rustle is a real thing, but it's that very interaction that kills the wave pattern. And finally, this experiment confirms this core idea of quantum mechanics with a clarity and a precision that's just never been seen before.
You know, the study's leader, Wolfgang Ketterle, he put it perfectly. He said that what was once just a Gedanken, a pure thought experiment, has now been made real in a lab. It's a testament to a century of unbelievable technological progress.
And so we're left with this strange, beautiful, and kind of unsettling core of quantum mechanics. It seems the universe doesn't actually have a single, definite state until we measure it. The active observation doesn't just reveal reality, in a way, it helps create it. And that forces us to ask a really mind-bending question. If reality itself changes when we look at it, what does it truly look like when we don't?